Good morning, sir. Yes.
Yeah. Yes, thank you. So in the timetable, we have scheduled MC 2004. So actually, I'm conducting a MC 2003 lectures, right? Because both the lectures are conducted by me. So I'll first discuss the network security. So in the weekdays, we'll have MC 2004. Uh, so right. So this lecture, this course will be conducted by me and Kenneth sir. So that's why actually I took it on Saturday. So I will conduct, two sessions like this, and finish up the my part of the course, and then the Kenneth sir can take over. And so most probably, I don't know whether we have it on Sundays. I'll try to take it to Saturdays. Because yesterday we had that inauguration program for the next batch, so that's why I took it on Sunday. So we'll see how it goes. So for the exam, from the exam paper, we are taking 60% out of the paper and 40% from the assignments. So there'll be a number of assignments for this course. Some might be practical, and so normally there'll be several take-home assignments from Kenneth as well, right? So most of my assignments will be in class. Some of them will be practical assignments, right? So that is the plan for the course. So you have studied network protocols in the first semester. So anyway, I will do a quick recap of some of those things just to brush up your memory, and we'll go to the network security part. So yes, so these are the topics that I have planned to discuss today. So just some brief introduction about the computer networks. So different types of networks, and the course title is network security. So we'll see what network security means, right? And some network protocols, the reference models. So you have discussed some of these things in your first semester in the network protocol course. So anyway, I will ask some questions from you, so you can give the answers, and we can have some discussion. So that's the plan for the first day. So we'll see how it goes, and let's tune our course. Right. So this is just a simple representation of a computer network. So as you know that in a network, there has to be more than one device. And so otherwise there's no need of a computer network, because network we need to communicate with several parties. So which means we need to have at least more than one device. So you can see that in this diagram, I have two N devices, so OS devices, this one and this, and we have some medium to connect those two devices, and sometimes there may be some intermediate devices, right? So these N devices can be anything like computers, maybe tablets, smartphones, likewise any of the devices, and this medium can be a wired medium, or it can be a wireless medium, right? So there can be different types of mediums that you can connect. If it is wired medium, then we have different kinds of wires, starting from the coaxial cables, then the twisted pair cables, shielded, unshielded, twisted pair cables, then the fiber optics. So likewise, we have some cables or guided media. That is one type of connection. And we have wireless communication mechanisms, starting from radio waves to the microwaves, then infrared, then visible light communication. And still, it is not wired communication. The visible light communication is there as a communication mechanism like that, especially the Li-Fi technologies. And so we have different mechanisms to connect these different media, sorry, the end devices, right? And we have these intermediary uh, devices like the switches, then routers and firewalls. So likewise, we have a number of intermediary devices. And so each of these devices, they have their own responsibility in the network. So they behave in different manners, right? So to provide whatever the service that you want. Right? So that is a basic introduction about the computer network. So you have discussed these things in your protocol lecture as well. So let's brush up our memory, and let's start our network security session. So yes, then when it comes to the networks, we have different sizes of networks. So starting from a very small network to a wide area network. So we have small home networks, office networks. So we have discussed some of these things in our network design chapter as well. Right? We have local area networks, then wide area networks, and as you can remember, we had different topologies, right? We had the logical topologies, then we had some the physical topologies. So a lot of things were there when it comes to these things. And the internet. So the very important point when it comes to the networks. So we have the internet or the infrastructure, right? So where you have connected all these devices, a vast network of devices, that is a combination of different local area networks and different wide area networks. So this is basically the infrastructure that you have. So whatever the other services, like web services and email services or other services, they run on top of this infrastructure, which we called as the internet, right? And then these different types of connections. So initially we had these normal telephone connections, right? Our infrastructure was actually built to do the telephone communication. So if you can remember, right, before 15, 20 years, we had that only the telephone communication, and we use a special device called a modem to do the data communication. But the problem was that the infrastructure was tuned to use for the voice communication. So the infrastructure was there only to do the voice communication or telephone calls. But later on, we need to do the data communication. So therefore, we use a special device called modem. So that modem was used to convert the data, or these ones and zeros, into voice communication, and we use the same infrastructure to send the data or connect to the internet. But there were some limitations, like at one time you can do only one communication, either a voice communication or a data communication. So, and the speed was very low, so it was 56K. So you can, some of you might have used the dial-up connection, so you can remember the experience of using a dial-up connection. So there were problems like that. So later on, to overcome these problems, they have introduced this DSL, which is the digital subscriber lines. So in the digital subscriber line, they use the same infrastructure, so which is used to do the voice communication. So they have used the same infrastructure, so they haven't changed any wires or anything else. They have introduced a new technology, that is the DSL. So when it comes to the DSL, what they actually did was they used the same communication medium, and they divide it into 256 different channels. So the channel, the bandwidth was 4 kilohertz. So you had 4 into 256 different channels, and you separate those different channels for different purposes. Example, you give one channel to do the voice communication, and several channels to do the uplink, and several channels to do the downlink. So likewise, you separate channel, separate the medium into different channels, and hand over different responsibilities for each and every channel. So with that, the people were able to do the voice communication with the data communication parallel, and they were able to get some more higher data rates. So that is DSL. And then we have the mobile communication, that is basically used to communicate with mobile devices and cellular networks, then the satellite communication. So these are different types of communication mediums, so different connections, right? And this network architectures. So we have discussed these network architectures in our previous lecture, the network design course, the hierarchical network architectures, the flat network architectures. So there are different architectures like that. So, and we have, you can remember, we had different requirements in when it comes to this network architecture, the scalability, the QoS things, the security, the fault tolerance. So likewise, we had different uh, requirements as well, the redundancies likewise. So we have discussed these things before. So anyway, I'll just brush up your memory, right? So the physical topologies and logical topologies, so I'm not going to discuss these things again, right? So we discussed these things previously. Right. Now this is the important thing, right? And I need your support here, right? Okay. Now, this is my question. As I normally I use this diagram in many cases. So this is a very basic computer network, and it has almost all the things that you required in a computer network. Right? Example, we have two host devices or two end devices. This PC0 and PC1. I use Cisco Packet Tracer to create this diagram. So this is PC0 and PC1, and we have switches and a router, right? So we have all the devices that we normally need to do a communication, right? So I'm going to send a message from PC0 to PC1, and so now that is my task. I'm going to send a message from PC0 to PC1. Now my question is, in this network, in this communication network, what are the interfaces that should have IP addresses to do the communication? right? So how we are going to get the answers? Yes, is there anyone who volunteer that to like to give the answer? Now I'm going to do a communication from PC0 to PC1. So I want to send a message from PC0 to PC1. So my first question is, what are the interfaces that should have IP addresses?
ADEH.
A, D, E, H. Okay, answer from
Thakur.
Taruk, right?
Yeah.
Okay, D, E, H, right? Any other answers? Right, okay. Okay, so the answer is correct. You need to have IP addresses on A, D, E, and H. Correct. Right. Now, so I'm going to prepare the message at this PC0. Right. Now, I need to have some information to create that message. So that information now, the source IP, then destination IP, then I need the source MAC and destination MAC, right? For information. Now these are the very important information that I need to have to create that message or datagram, right? Now, can you tell me these details? So, um, yes, what is the source IP? So let's assume that all these interfaces has IP address. If let's say IP address of this A interface is IP address of D is IP is IPE, IPH, and MAC is MAC A, MAC D, MAC E, MAC C, MAC B, likewise. So let's assume that we have IPs and MACs like that. So what is the source IP address? Yes, I'm checking the chat as well. So if you have your answers, you can put it in the chat as well.
It's IPA.
Yes, A. Okay. This is IPA. So what is the destination there? IPH. Okay. Now this is the question. So what is the source MAC? Okay, Devaranjan says
A.
is MAC A. Right. Then destination MAC. Okay. Yes. So all of you agreeing with this?
Destination MAC.
Yes.
B.
Okay, we have several answers. MAC B. Okay. Any other answers? I think all of you are agreeing with this. IPA is the source IP address, and IPH is the destination IP address. So there are no answers. I mean, no second answer for this. Only MAC-K. The problem is destination MAC. So now we have two answers. Any other answers? Samira says
Not D, it's D, no?
Sorry?
Could be D, no?
Okay. MACD. Okay, so let's take a vote. So people who are saying MAC-H, please raise your hand. No one says MAC-H. Okay. What about you, Devaranjan? So you gave the answer as H. Okay, then people who are saying it as MACD.
So it's D, no?
What you are saying? B or D?
D, no?
Can
I
you
think
put it in the chat?
D.
Say D, sir.
Tisara saying D. Okay, Mac. Mac D.
Yeah, Tagore also trying to say D, so not B.
Right. Okay. D. Right. We have now several answers. Okay. Now people who are saying D, can you raise your hand? Right. Now the actual answer is D. Right. It's Tarindu and the is Takura. Yes, D. So D is the correct answer. So right, so let me explain it before moving forward. So now this is what it actually happens, right? So I will show you the simulation as well, so you can get some clear idea with the simulation. So in order to do a communication between so to do a communication between two devices, let's say this PC0 and PC1, first thing is you need to know the destination, right? So as an example, if you want to log into your Facebook account, then you go to the address bar and type facebook.com. So that is your destination, right? So you need to know the destination, so where you need to go. And so that is one thing. That is your destination, right? So destination, normally we type it as a web URL, right? Let's say facebook.com. So that's what normally we type in our address bar, right? So as you all know, this is only for us, right? So this is the human readable format, facebook.com. But this is anyhow converted into an IP address, right? Maybe something like this by using a DNS service. So it will be converted to IP address. So which means we need to know the destination IP address. So without knowing the destination IP address, uh, we can't do or we can't initiate a communication, right? So definitely you need to know the destination IP address. So in this case, that destination IP address is IPH that we know, right? So and without knowing it, actually we can't initiate the communication, right? So that part is clear. So IP addresses we know, IP we should know. Otherwise, we can't initiate the communication. Now, then when we create that datagram or message, if you can remember the OSI layers, I think in your the protocol lecture, you have discussed this OSI layers. I think I have some slides about the OSI layers as well in the end of this session. So in the OSI layers, you have 7 layers. So let's assume that first 3 layers as application, and then you have the transport layer. So I consider all 3 layers, the top layers as application. Then you have the transport layer, then the network, then you have the data link, and finally the physical. So these are the layers that you have. So your message comes from the application layer. Maybe it will be a HTTP request, right? So in the application, you will use HTTP. So then whatever your message comes to the transport layer, right? So in the transport layer, you need to, decide what is the protocol that you are going to use. So basically, when you are using HTTP, then you have to use TCP at the transport layer, right? And you decide whatever the protocol that you're going to use. It can be UDP or whatever the transport layer protocol. And in here, we add very important information, that is the port numbers, right? So which means each and every application has its own port number. So example, if you consider web server has port number 80. And so likewise, we have some well-known port numbers. And in your site, your whatever your application will get a random port number, right? So you can have port numbers till 65,000 odd port numbers, and we have around 1,000 well-known port numbers. So whatever your application will get a random port number higher than 1,000, 1,025, right? So those are the port numbers. So in the transport layer, you add source port and a destination port to the headers, the transport layer headers, and you simply wrap the message and send that message to the network layer, right? So in the network layer, we have protocols like IP, IPv4, IPv6, like we have some IP related protocols. Then there you add the source IP and the destination IP address to the headers, right? Now to put these things, right, you need to know the destination IP address. So you know the destination IP address. Maybe you add the destination IP address, so you will get the destination IP address from the DNS services, right? So the destination IP address, you know it, and the source IP address is your own IP address. So this is okay. This is clear. We have that information. So we put the IP headers, wrap the message, and then send it to the data link layer. So there's a special name for this process, and I don't know whether you can remember it. We call this as encapsulation, right? You get the message from upper layer, wrap it, and send it to the next layer. Then you put the headers and wrap the message and send it to the next layer, right? So this is the encapsulation process. Now the problem is with the data link layer. You send whatever the message from the network layer to the data link layer. And in the data link layer, we have protocols like, let's say, Ethernet, right, or Wi-Fi. Right? So we have some data link layer protocols. And this data link layer, we have to add the header as well as a footer. I'm not going to discuss those things. So, because I have to discuss from the protocol lecture. So, data link layer, we have protocols like Ethernet, Wi-Fi. So, that protocol selection is based on the medium that we are going to use. So, if it is wired medium, then most probably you have to go for protocol like Ethernet, right? So if it is fiber, then there are fiber related protocols. And if it is wireless, it can be, let's say, if it is a Wi-Fi network, then you have to go for Wi-Fi protocol or Bluetooth. Likewise, you have to select whatever the protocol based on the physical medium, because we are very close to the physical medium now, right? So after the data link layer, you have the physical layer, which means we are very close to the physical layer. So you have to select the protocol based on the physical layer that you have. So let's say we have now this link is wired network, right? So let's say we are selecting Ethernet, right? So Ethernet is our protocol. Then we need to have two important information, that is source MAC and destination MAC, right? So those are the two main information that we need at this moment. So when you consider the other thing, the data link layer, so let's say the transport layer, the network layer, the application, so they all do what we called as the end-to-end communication, right? So you are communicating from this device to the other device, that is PC0 to PC1. So that's what all these layers does. So the application of your device will experience that it is actually communicating with the application of the end device, PC1, right? Because all the other things are covered. The application will see abstract information, right? So it experience that it is communicating with the PC1. That's all. So transport layer protocol, the TCP will see or observe that it is communicating with the transport layer of PC1. The network is the same, so it is communicating with the end device. But the problem is actually in the network you have to communicate by hop, right? So your message has to send to the router. The router has to forward the message to PC1. So there are multiple hops in the communication. So that hop-to-hop communication is done by the data link layer, right? So that's why we need to know the MAC address of this interface, because we are forwarding the message to this interface. And so that will be handled by the data link layer protocol. It can be Ethernet or it can be Wi-Fi. So whatever the protocol in the data link layer needs to deal with the hop-to-hop communication, right? Because network, transport, all these things, these protocols, they deal with end-to-end communication. So they are not going to worry about what is in the middle of the network, right? So is it clear for you? So that's why the difference in this MAC addresses and the destination address, MAC address and the IP addresses. So the IP addressing, IPA and IPA, that's correct, right? So the source IP is IPA, destination IP is IPH. That's done, right? But when it comes to the data link layer, you have to deal with hop-to-hop communication. But then you will think that why this switch? So why we are going to miss it, or why we are going to jump over the switch and directly go to this interface? The reason is the switch interfaces, they don't have MAC addresses, right? So these are, we call them as switch gears, right? Not actually it's ports. So we have this switch, let's say ports. So they don't have MAC addresses, right? So whatever the message that we send to the switch, simply it will going to broadcast the message. And so let's assume that this is a hub, not a switch, this is hub. So if it is a hub, what it does is when we send the message to the hub will broadcast the message to all the interfaces connected, all the interfaces in the hub. And so all the devices connected to the hub will receive the message, right? So we are not going to worry about this. So somehow you need to go out from your network to connect to the other device, right? So if you are, so when we configure in this device, normally we put default gateway. So that is where if you want to go out from your network to the other networks, then you have to go through the default gateway. So normally this destination MAC address will be the MAC address of the default gateway. Because we are going to send the message to default gateway, then it will forward it to the other network, right? So that's why this destination MAC address is the MAC address of the router interface, not the MAC address of the final destination. The reason is we don't know the MAC address of the final destination, and we need to deal with this hop-to-hop communication. So if it is a very complex network, then this first link will be wireless link, and the second link will be fiber link, and maybe the third one will be, let's assume that it is a coaxial cable, right? So you will have different mediums. So first in this communication, you have to use Wi-Fi network, right? And the next one, you have to use a fiber protocol. Then you have to use maybe Ethernet or something different protocols, right? So from each and every communication, you are changing the protocol, and you need to deal with the source MAC address and destination MAC address. It's going to change, right? So when the message comes to here, so the source MAC address will be E and the destination MAC address will be H, because we are dealing with the communication from here to here. That's all in the data link layer. So the data link layer, you are dealing the communication from this device to this interface. That means from A to D. That's all. Then E to H, right? So that is the thing that you have to remember when it comes to the data link layer, right? So is it clear? So do I need to explain it? If it is not clear, please tell me, right? So I can explain it. I will show you some. Give me a second. I will show you some simulations, so then it will be easy for you. And the other thing is, there's another protocol that you need to do this thing. That is the ARP protocol, ARP, Address Resolution Protocol. I think you have discussed that in the protocol lecture. So which used to get the MAC addresses, right? So you don't know the MAC address of D. So in that case, you simply put the ARP message to get the MAC address of D. Right? So ARP is again very useful. So is it clear? Or if you have any questions, please ask. So we need to clear up all these things before discussing some advanced security related things. Is it okay for you? So if it is not clear to you, tell me when we have a physical lecture. I will use the board and explain it again. And if you have any other questions, please ask.
So can you explain that again, that why destination MAC is MAC D, that the two reasons?
Yeah, okay. Let me show you give me a second. I think I have a simulation. Okay, so can you see my screen? This is a very simple networks. I have created it using the Cisco packet tracer. And these are the IP addresses. I have configured all these IP addresses. And you can see that these are two different local area networks, right? So this is 10.0.1.0 network, and this is 10.0.2.0 network. So two different networks, right? And I have two end devices in this network, and this is a switch. The same setup is there in the other network, right? Now, let's say I'm going to communicate from this PC2 to PC0, right? So my source IP address has to be 10.0.1.1. This is the source IP address. And the destination IP address has to be 10.0.1.10. So that is clear, right? So two devices, and this source IP is this IP address. This destination IP address is this IP. So that thing you need to know, right? So the other part is the MAC addresses, so which is dealing with the data link layer, right? So now the problem is we don't know the MAC addresses, right? So in theory, it has to be globally unique, right? So each and every device should have its own MAC addresses, right? But the problem is so we don't know the MAC address of each and every device. And the other problem is at one moment, this 10.0.1.10 IP address will be assigned to this PC0, but in the other case, this 10.0.1.10 will be assigned to another device, right? So we don't have a mechanism to keep a directory which has the IP addresses and MAC addresses combinations, and because this can be changed. So at once, so let's say you came to UCSC and you will receive IP address, right, from our DHCP, right? And after you leave the UCSC building, after some time, that IP address might be issued to another device, right? So different MAC addresses. So we can't keep directory, a global directory of MAC addresses and IP addresses, right? So the solution is using another protocol, which is ARP, that is Address Resolution Protocol. So in the Address Resolution Protocol, what we do is we simply send a message asking about the MAC address relevant to the IP address. Right? So I will show you it from the simulation. Right? So before creating our original datagram or whatever the message that we are going to send, we need to find the destination MAC address. So to do that, we use the ARP protocol. Right? So let me show you how it happens. So I will go to the simulation mode, and let's go to this machine, that is PC2. So I'm going to ping, right? So you might not see what I'm typing here because the font size is very small. So I'm typing ping 10.0.1.10. That is this IP address. So I'm in this device now, the PC2 device, and I'm going to ping to this. Right? I think you know what is a ping command, right? So I'm going to ping to this. So now I have just started my ping, and you can see that there are two messages generated at this device, right? This black color one is the ICMP message. So to do the ping, we are using the ICMP protocol, right? Now this is the ICMP message, and this is the ARP, right? So let's go to the ICMP first, right? Now, can you see that 7 layers? Layer 7, 6, 5, 4, 3, 2, and 1. Now we have layer 3 information. So layer 3 means the IP information. So we have IP source, that is 10.0.1.11, which is this IP address. And we have the destination IP address 10.0.1.10, which is this. Now source IP and the destination IP address are there. Now we know that. Is it clear, Lakshi? Right? So we know that 2 IP addresses. Right? Because without knowing the destination IP address, we can't initiate the connection. And we know our own IP address. So source IP address and the destination IP address are known. So straightforward, this machine can create the layer 3 headers. That is done. Now the problem is we don't know the destination MAC address. So we need MAC address in the layer 2. So we don't know the destination MAC address. So that's why it is blank for now. Now what this device does is it creates the ARP. So this is the ARP. Now ARP is running in the layer 2 and it is simply creating an Ethernet header, right? And this is the source MAC address. That is my own MAC, this PC2's MAC address. Because it knows its MAC address, so it can put the source MAC address there. And the destination MAC address, it doesn't know. So what it does is, it put all F in the destination MAC address. So all F in destination MAC address means it is a broadcasting message. Now what this device is going to do is create a ARP message and simply broadcast it, right? So in this ARP message, what is it asking is, who is 10.0.1.10? Now that is the question asked in the ARP message. And you are going to forward it. So that ARP message goes to all the devices in the network. I mean, all the devices connected to the local area network, right? So ARP messages, they are not going to router, right? So they will only broadcast in the local area network because it doesn't have layer 3 header, right? So without having a layer 3 header, you can't go out from the network. So it will be broadcasted within your own local area network. That means within this network, it will be broadcasted, right? And it asks the very simple question, who is 10.0.1.10? Now let's run the simulation and observe it, right? Now the ARP message comes to the switch, right? And after that it broadcasted. Can you see that? It broadcasted. So it has only 2 links remaining because it is not going to broadcast back to the source port, right? So it will be broadcasted to all the remaining connection or remaining ports in the switch. Now in here it says that it is discarding the message because it is not IP 10.0.1.10. It is 10.0.1.1, right? So it will simply discard the message. But you can see that the machine with IP address 10.0.1.10 has accepted that ARP, right? Now it has accepted the ARP and it is going to reply for it, right? Now the message delivers to the 10.0.1.11. And after that, it can create the ICMP message, right? Now it knows the destination MAC address. Now it will be forwarded, right? Now the ICMP is delivered. First ping claims. Now that is within the same network, right? So is it clear? Within the same net, the communication within the same network. So everybody okay with that? How the IP addresses work and how the MAC addresses work.
Yes, sir. Now clear. Thank you, sir.
Okay, right. Now the problem is when it goes to the when you are going to communicate with the other networks, right? So let's say you want to communicate from PC2 to PC3, right? So again, let me show it using the simulation. So I'm going to communicate with this one, 10.0.2.10, right? So ping 10.0.2.10. So again, I'm going to start the communication. So let's see what happens. Now it is going to send that message, sorry, the ICMP. Sorry, we have to wait. So ignore these things. These are some span protocols. So to go out from your network, you have to configure the default gateway. So I haven't configured the default gateway. That's why. Okay, so let's use this device. So I'm going to use this and ping to 10.0.2.10. Right. Again, you can see that it has created two messages. So first is the ICMP, right? And second, again, an R. Now this is important, right? So I'm going to communicate with 10.0.2.10. Now that is my destination, right? But in this ARP request, it is asking the IP address, sorry, the MAC address of this IP, that is 10.0.1.1, which is this interface, right? Not this, right? It is requesting the MAC address of this interface. Now this is very important. So if you can remember my previous failed attempt, so there I didn't configure the default gateway for this device, right? So that's what has happened. So if you want to go out from your network, you have to configure the default gateway, which means it is the place where you are going out from your network, right? So to go to 10.0.2.0 network, you have to go out from your 10.0.1.0 network, which means this one. So you have to go out from this network to go to the 10.0.2.0 network, right? So to go out from your network, you have to go through the default gateway. So that we have to configure beforehand. So in each and every device in your network, you have to configure your default gateway. Otherwise, you can't go out from your network, right? So that part you have to do in your devices. Now, what the protocol does is, okay, my destination IP address is not within my network. Therefore, I have to go out from my network. So to go out from my own network, I have to go through the default gateway. So that is the logic of the device, right? So to go out from the network, you have to go to the default gateway. So that's why my device, so this PC0 is trying to forward that message to the default gateway. So if it is go to the default gateway, then the rest will be handled by the routers and the routing protocol. Now the only responsibility of this device is to forward that message to the default gateway. Now that is what it's going to do, right? Now let's run the simulation. So ARP message comes, it will be broadcasted. And PC2 is going to ignore that because it is not 10.0.1.1. So router interface will be replying for the top message, and then you can create the ICMP. Now, our ICMP, if we check the ICMP, now it has some destination MAC address and it goes to the router interface. And you can see that message has again discarded, right? Because the IP addresses are different. In the ICMP, the IP address, the destination IP address will be 10.0.2.10. But the message comes to this and there's an IP address different. So again, your router, what it does is, it sends the ARP asking the IP address of, asking the MAC address of this. That is 10.0.2.10, right? Now, the router is doing the ARP, sending the ARP request. And it gets the MAC address of this device. Now the router has the MAC address of this device. So again, let's ignore these things. Then the second ICMP message comes. So you can see that the first ICMP, the ping has timeout, right? It didn't go to the final destination. Now you can forward the message to this. And if you check this ICMP, it has the MAC address of this device, right? Now from here to here, it uses a separate set of MAC addresses to forward the message. And from here to here, it uses a separate set of MAC addresses to forward the message from here to here, right? So two different set of MAC addresses. Now is it clear? So that's why these MAC addresses change each and every time, right? So if it is not clear, so please record the problem and I will explain you it once we have a physical lecture, because I can use the whiteboard and explain you it again, right? So hope it is clear. So if not, please wait and we'll discuss it back again when we have a physical lecture, right? So Lakshi, is it clear for you? Is the doubt clear?
Yes, sir. Thank you, sir.
Okay. So this is very important thing in computer networks, because if you can explain this, if you know how the message passed from one node to the other, then you know networking, right? So you have the idea of networking. All the other things are just protocols, right? All the other things are just how the protocol works and protocol standards. So if you consider Ethernet and the Wi-Fi, so there are some slight differences or slight changes, that's all. But what it actually does is same. So it is going to forward the message from one node to the other node. That is it will forward the message to the next hop. That's all. So that's what the data link layer protocols does, right? So data link layer protocol might be different, right? So it can be Bluetooth, it can be Wi-Fi, it can be Ethernet. And so the protocol might change, but what it does is same, right? So it will forward the message from this node to this. And so if you consider the TCP or IP or the transport layer protocols or the data link, the IP layer protocols, they are handling the communication from this node to this, end-to-end communication, right? So therefore, the IP addresses are not going to change. If you have some kind of NAT or something like that in the middle, then it will change. But let's say you don't have any middle boxes like that, then you are dealing with end-to-end communication. So IPA and IPH, right? If you consider transport layers, the port, source port and destination ports. So it is not going to change in the middle of the communication. But in the data link layer, you are dealing with hop-to-hop communication, which means from this to this and from here to here. So two hops. And so in that case, you are dealing with this. So in the data link layer, you are dealing with this hop to this hop, right? So in this communication, in the first communication, source MAC will be this, and the destination MAC will be this, right? And this communication, the source MAC will be this, and the destination MAC will be this. So two separate communications. But if you consider the IPs, then you are doing a end-to-end communication, right? So from here to here. So source IP will be this, and destination IP will be this. So it doesn't care about the middle boxes. It doesn't know that the router exists. It doesn't need to know, right? Because it is dealing with end-to-end communication, right? So the data link layer protocol, so they are doing the hard work, right? Because they are the protocols actually forwarding the messages from here to here and here to here, right? So data link protocols are the actual communication protocols which deal with the real communications, right? So all these things are just abstractions. So IP, the TCP, all these things are just the upper layers, right? I hope it is clear. If not, please ask it again, right? Once we meet. Right, so that is a very simple network. Right? So you need to know how the network works, right? So when you are studying the network security, you need to, so beforehand, you need to have some idea of how the network works, right? Okay, now let's see some new trends in this computer networks domain, right? So the first one is this BYOD, not BYOB, right? So this is BYOD, bring your own device, right? So most of the organizations, some of the organizations, right? So some of the organizations, they ask you to bring your devices to the office, right? Not asking, so they allow you to bring your device to the office, and they allow you to connect your own network, sorry, own device to the network. And so that is one such new trend that we are having. But some organizations, they don't allow it. They give their own laptops, so they give their own machines to work. And so, and they are not allowing you to bring your own laptop and plug it to the network, right? I think some of your organizations might allow you to bring your own devices, and some might not. So that is a new trend in this computer network domain, but it comes with some security risks, right? So we'll discuss them later. So at once you can understand that when you are allowing people to bring their own devices and plug it to the organization network, then if there are any malicious programs running in your personal device, they might affect the network of the organization, right? So simply you are allowing the viruses or maybe malicious applications to bypass your firewall, right? Because you are connected to the internal network, then it will affect your the network. So if you are allowing to bring these other devices to the network, then you have to think it before, and you have to have separate security mechanisms to handle those things. So the architecture wise, you have to think about it beforehand. So this is one new trend. And the other thing is online collaboration. So that actually started very I mean, in large scale when we have the pandemic situation. So online collaborations were there and the video conferencing. So a lot of people were at different locations, let's say outside the organization, and they are having, they are working in their office work outside the office environment, and actually they are having meetings outside the office environment. So that is good for people because they don't need to come to the office environment to do their work. But if you consider it from the organization's perspective, it might not be good because you are doing some critical meetings, or you are getting some critical meetings, you are taking some critical decisions, you are discussing some very, I mean, things which are in your organization, staying outside of the organization, right? So that is not good in the sense of security. Actually, we are doing some research on these things, these areas, these days, right? So with some students. So especially when we are having a conference call or video call, and if you are discussing some critical matters, so whether it is secure or not, so there are some security risks. So even you might have that experience if in your home, if two people are working in two organizations, then you can hear the others' Zoom meetings, right? So you can hear what they are discussing. So that might not be good because sometimes these meetings before the COVID, we are taking these meetings inside the meeting room, right? In a boardroom. So no one else can listen to the meeting, or no one else can listen to the discussions, and no one else will know the decisions which were made. But after this pandemic, because of the online collaborations and video conferencing, sometimes one of the board member will be in a coffee shop, right? And the others might can hear what the people are discussing in the board, right? So those are security risks. So because of these new trends, we are actually facing some new areas of uh, security problems, right? So some of the issues or some of the problems are not technical actually, right? So that meeting problem is not a technical issue, right? So if you consider it from the technical perspective, maybe the connections are encrypted. So there will be some end-to-end encryption in the video call. But the problem is once it comes out from your device, so we are going to protect it, right? Maybe let's say as an example, right? So husband and wife are working in two software companies. Maybe they are bidding for the same project, right? So the two people can listen to the communication of the two companies, right? So that can happen, right? So the security issues are there with these new trends. Then cloud computing. So most of the organizations these days they are going from on-prem to the cloud, and some of the organizations they are coming from cloud to the on-prem. So I have got some information that some of the organizations are actually coming back to on-prem. So anyway, so there are different trends for each, and so different times people think that okay, going to cloud is the best solution, and later on they will decide let's come back to on-prem. So likewise that changed, but this is kind of new trend going for cloud computing. But still yeah, the cloud computing is kind of a new trend, and I have discussed with some of the organizations, and what they told is the demand is very high in these days. The cloud computing, the demand is very high, and even if they turn down one of the, let's say, Azure VM, then it is very difficult to turn it back on because of this high demand. So the hardware resources are very critically using, right? So because of that, because of the high demand, it is kind of difficult to turn the VMs back on, right? So still we have a huge demand on cloud computing, and which comes with a lot of security problems, right? So these are some new trends in the computer networks and this computer domain. So as security people, we have to think about these things, and we have to think about the security risk comes with all these new trends. So when it comes to the new trends, maybe the company or the organization management, they try to move with the trend, right? So if one company allows to do this BYOD, then might be the other companies, the top management also think, why not? Let's ask our colleagues or our employees to bring their own device and plug it to the network. But they don't see the risk. They don't see the potential problems with that, right? So in that case, the technical people has to handle those things, right? So I think you have that experience because you are working in the industry, so not like me, right? So you have that. I think you have that experience. Right. So let's see some security threats. Right. So I know that you have read about these things and you have studied about these things. So just I have put a slide there about the network security. So there are a lot of security threats, right? So starting from viruses, Trojan horses, spyware, adware, right? So there are a lot of security threats like that, and the zero-day attacks, right? So that is the first day that whatever the vulnerability becomes, I mean, people get to know about that vulnerability, right? So maybe you might have some threat actor attacks, that is maybe a malicious person attacks your network or your devices. So denial of service attacks, right? Then data theft, right? Identity theft. So there's a number of security threats that you have for organization, and can have some solutions. So we'll discuss these things one by one later. Right? And we can have firewalls, the antivirus softwares, right? And we can have access control lists, and we can have like IPS, IDS, intrusion prevention systems, intrusion detection systems, right? So we can have those kind of things in our organization, and we can specially train the people, right? To work in the network, then with the devices, then can set up VPNs. So a lot of things are there, right? So yeah, we'll discuss them one by one later. Right? So since this is the introduction session, I will just go through these things. Right. So network protocols. So I'm not going to discuss that in details because you had a separate course for that. Right? But when it comes to the security part, so you need to have good idea about the network protocols. So we have a separate section or topic with SCATI. So in SCATI, we are going to create our own network messages or network packets. So in that case, you need to know what are the things available in this network protocols, the headers, and how the network protocols work. So therefore, the knowledge about network protocols is very important in this case, right? So message, I will go through these technical terms. So this, what do you call this? Keywords, just very quickly. So you will brush up your memory. Right? So message formatting and encapsulation means that in a so in the network that we can explain the network by using this layered architectures, right? So if you consider as a basic example the OSI layers, we have 7 different layers, and whatever the message is coming from the application will forward to the transport layer, and that message will be sent to the network layer, and again it will send to the data link layer. So likewise, the message will be sent from upper layers to the bottom layers. So message formatting and encapsulation means, so whatever the thing you get from the application will be the data for the transport layer. So in the transport layer, we have transport layer headers and the data portion. So header information will be filled by the operating system, and the data will be whatever the data you get from the application layer. And you send this entire thing to the network layer, and that entire thing will be the data for the network layer, right? So the network layer put headers on top of that data, and it will send that entire thing to the data link layer. So for the data link layer, the data will be the entire thing which you get from the network layer. So that is the formatting and encapsulation. So you encapsulate each and every message within your headers and send it to the next layer, encapsulation and formatting. So message encoding comes in the physical layer because you are getting messages in ones and zeros. Yes, in the computer you have everything in ones and zeros, binary. So these ones and zeros has to be converted into a different kind of signal. So we have electrical signals, we have light signals, we have microwave or some kind of wireless signals. So that's ones and zeros has to be converted into that medium or format. So ones and zeros has to converted into the electrical signals, and ones and zeros has to connect converted into light signal. The ones and zeros have to convert into microwaves. So that is the encoding part. So as an example, let's take a very basic example. You are going to represent binary 0 with low voltage, binary 1 with high voltage. So that is encoding. You are going to represent binary 0 with bulb off. You are going to represent binary 1 with bulb on. So that is encoding, right? So encoding is conversion of the signals into a different format. And you do the other way around, that is decoding. So when the message comes to the destination, it comes in as electrical signals, high voltages, low voltages, high voltages, low voltages. Then you convert that high voltages back to binary 1, low voltages back to binary 0. Right? So it is the encoding. So we have different ways of encoding, right? Manchester encoding. Likewise, we have different encoding mechanisms. So they encode these ones and zeros to whatever the signal that you are using in the physical medium, right? Then message sizes. So each and every protocol, they have different message sizes. So normally we define the maximum message size, right? So or maximum segment sizes, right? That is MSS. So there's a maximum size for the message, but in the data link layer, especially in Ethernet protocol, we have a minimum size as well. So I'm not going to discuss what is the reason for having minimum sizes, right? So it is actually to reduce the collisions and all the problems in the data link layer. It has some mechanisms like that. So a minimum size as well. So we have maximum sizes and minimum size of the message. So all these things are defined in the protocol. So then the timing. So how you do the flow control. If you consider the TCP, it is dealing with this flow control. It has a different condition controlling mechanisms, right? So it deals with the flow control. Then response timeout. So again, especially in TCP, you are waiting for some acknowledgements, and if you do not get that acknowledgement within the time period, then you retransmit the message. So response timeout is there. And you have different access mechanisms. So how we are going to access the medium, right? So all these things are defined in network protocols, right? So that is what we call as these protocols, right? And we have different types of network protocols like communication protocols, security protocols, then routing protocols, service discovery protocols. So let's take some examples like communication. We have TCP, UDP, HTTP, likewise communication protocols. And security, we have, let's say, TLS, SSL, SSH. So likewise, we have some security protocols. Then routing, we have OSPF, IGRP, IGRP, likewise RIP, RIP, right? So we have routing protocols. Then service discovery protocols like the DNS, DHCP. So those are just service discovery protocols. We have number of network protocols and they serve different purposes, right? So I'm just going through these things just to brush up your memory, right? So different protocol suites, example, the OSI, TCP, AppleTalk. AppleTalk is proprietary protocol of Apple, so it is not using the with the common people, right? So with the normal devices, you don't have it, right? So OSI, the TCP is kind of a very popular protocol suite, right? So OSI layers, 7 layers, and TCP/IP you have 4 layers, right? So this is that encapsulation process, right? So you get the data from the upper layer, and the TCP headers, you put the TCP header. Then this entire thing will be data for the IP. So IP, put the IP headers, and this will be the data. And for the Ethernet layer or Ethernet protocol, the entire thing will be data, right? So if you consider the TCP, so for TCP, this is the only data, right? When you consider the IP, so IP, this entire thing will be data for the IP, right? So this entire thing will be data for IP protocol. And for the Ethernet, again, this entire thing will be data, right? And Ethernet, you have that the tail as well, because we are dealing with some CRC checks there. Right? So this is the encapsulation process. And so comparison with the two models, OSI and TCP. So you have the same story. So you have the same computer network, but how we are going to categorize those process is the difference. So in the TCP/IP model, all this application, presentation, and sessions, so all the functions given by these 3 things will be categorized under application in TCP/IP model. The transport the same, so whatever the services provided by the transport layer will be same in the TCP/IP model. So whatever the services provided in network layer will be renamed as internet. And all the services provided by data link and physical will be categorized as network access in the TCP/IP model. So that's all. So it has the same network. So both these models is explaining the same computer networks, but they categorize the functions in different ways. That's all, right? So again, this is one of the major things that done in the transport layers, having sequencing and segmentation. So whatever the data you get from the application will not going to be sent as a stream in the wires. So it will be segmented. So you have that maximum segment size. So you use that maximum segment size and segment the data into small segments. And after that, you have to label those things. So that is the sequencing. So sequencing and segmenting will be happen in the transport layer. And this is just PDU. So we name these things in different ways. So in TCP, we called it as a TCP segment. In IP, we called it as packet. And in Ethernet, we call the entire thing as IP. So the Ethernet frames, right? So just names. Then different link access methods, the layer 3 address and layer 2 address. I show you this in, with the simulation, right? Okay, so the next thing is the Wireshark. So I think you all have some experience with the Wireshark, right? So we use Wireshark here and there in this course. So do you have access to your LMS? Do you have the course?
Yes, sir.
Okay, right. Thank you. So network security, right? Mhm. I will put some. First of all, have you have, please hands up that you are familiar with Wireshark? People who are familiar with Wireshark, people who have used Wireshark before. We have few. So if you please raise your hand if you haven't used Wireshark before. Never used Wireshark. Using last lecture only. Okay. What is the course? The protocol course. Ah, right, in my course. Okay, then that's fine. Okay, so I will put some PCAPs. I don't know whether I have given you these PCAPs. So just I will give you some PCAPs. So uh, try to play with them, and we'll have a small break and restart the session back. Right, so I have uploaded some PCAPs to the LMS. Please download them and try to play with it and see what are the information that you can extract, because we'll use Wireshark here and there in this course as well, right? Okay, then shall we get a small break and come back? So I'll keep the meeting running, and we'll meet, let's say, 10 caps before as well. So so there may be some situations where we need to use Wireshark here and there in the course, especially when we are working with Scapy. So we need to use the Wireshark to check the communication. So likewise, we use Wireshark in different locations of the course. So yeah, the next, the physical layer. So as I told you, the encoding part will be happening the near the physical layer, because all the information will be comes from the upper layers as ones and zeros. So that ones and zeros will be converted into a kind of signals. It can be electrical signals, or it can be light signals, or can be microwave signals. So whatever the signals, it will be converted near the physical layer. So that is the encoding process. Then in the physical layer, we have these different characteristics of the physical layer, like the bandwidth, then the throughput, the goodput, and the delay, the latency. So all these things are related with the physical layer. Right? So when we are selecting mediums for the physical layer, we have to think about our requirements. So what is the bandwidth requirement and what is our latency requirement? So likewise, we have to think about these different requirements, and based on that, we have to select the required physical layer medium. So we have wired mediums and wireless mediums. So so when it comes to the physical components, we have different devices. So encoding, like I told you, there are different encoding mechanisms. So one of the example is this Manchester encoding. So we have electrical signals, the light signals, the microwaves, the latency, throughput, goodput. So all these things are there when it comes to the physical layer. Right. This is one example of Manchester encoding. So you can see how the signal is encoded to the wire. So this is the message that we are sending 0, 1, 0, 0, 1, 1, 0. So that is the signal that we want to send. And you can see that we have some time or a clock signal. This is the clock signal. And you can see that in the middle of the clock, so it changed from high voltages to the low voltage. So if it changed from high voltage to a low voltage, that means it is binary 0, right? And if it is changed from low voltage to a high voltage, that is binary 1. And so that's how it is encoded in Manchester encoding. So again, high voltage to low voltage means binary 0. And again, high voltage to a low voltage, binary 0. And low voltage to high voltage, binary 1. A low voltage to high voltage, binary 1. And high voltage, low voltage, binary 0. So that is, it shows the conversion. So from high voltage to a low voltage is binary 0, and low voltage to a high voltage, binary 1. Right? So this is Manchester encoding, and there are different kinds of encoding mechanisms like that. Right? So you can check in the internet, so you will see different examples of that encoding mechanisms. Right? So wired mediums and wireless mediums. So when it comes to the wireless, so it is kind of a critical situation in computer networks. So a lot of security issues there when we comparing with the wired mediums. So there are a number of security risks uh, comes with the wireless medium, right? So the reason is in wired mediums, you can actually see the physical medium that you are connecting. So as an example, if you want to connect your device to the network using wired medium, then you have to plug a wire to your device through the RJ45 port, and the other end of that wire needs to be connected to a switch or maybe a wall adapter, right? So anybody in the surrounding can see that your device is connected to the network because there's a physical medium which you can see. But the problem with wireless mediums is you can't observe that there's a connection between your device to the network access point. It is invisible. So which means anyone within the range of the access point, anyone within the range of that signal range of that access point can connect to the network, right? But it is invisible, so nobody can see that the person is connected to the network. So that particular device will be authorized device or unauthorized device. So yes, there are security mechanisms, right? So we'll discuss about those things in the wireless network security session separately. There are mechanisms, but still you can easily break those security mechanisms and connect to the network. So if the intruder of the or if the attacker is within the coverage area of the network, they can they can get the access to the network. So it is not possible in the wired medium, because definitely you have to plug your device to the network. So in that case, if we somehow secure the network switch, right? If you, let's say, you put it inside a cabinet and if you lock it, then there's some physical security. So you can give some physical security to the network switch, and with that you can cover it from a lot of network security problems. But when it comes to the wireless network, it is open and nobody can see that the attacker is connected to the network. So that is a problem with the wireless network. And there are some other things like the coverage area. So each and every network, the wireless networks, it has its coverage area. So from a certain distance, so there's a certain distance from the access point that you can access to the network. Even there are different ranges, like there's a range from the access point where you can use the network and you can connect to the internet. So you can work without any issues. But there's a certain point where beyond that, you can actually weave the SSID or you can weave the network and sometimes you can connect to the network, but still you can't use it. You can't go to the internet. Right? So the signal strength is not enough to use the internet, but still you can see the network. Right? I think you have that experience. So you see the network, you can connect to the network, but you can't use it. So that is one region. And again, beyond some point, you can't even see the network, but that signals are still there surrounding you, and that will become the interference to the others, right? So there are, if you consider a location, if you consider your office location, you can see that there, if you check or if you scan for Wi-Fi networks, you will see that there are a lot of Wi-Fi access points surrounding you, right? So the problem is all these network access points use the same frequency range, right? So Wi-Fi, they are working in the same frequency range, 2.4 gigahertz something range. So all the networks are using the same frequency range. So which means each and every access point or each and every network is interfering others, right? So that is another problem in the wireless network. So there are a lot of interferences. And the security, so as I told you, we have to deal with a lot of security issues, and as well as we have to introduce a lot of precautions to avoid those security problems, right? So because we can't see the intruders because they can also connect to the network, and still it is a broadcasting medium, so anybody can capture whatever the messages that we communicate. So anyone can capture these signals and decode whatever the messages that we are sending. So a lot of security issues are there, so we have to provide that is, there's an extra burden that you have to put some security measures when we compare with the wired network. Sorry. And the next thing is, it is a shared medium. Right? Sorry. So as I told you, it is a shared medium. So everybody within the range can capture whatever the messages that you are sending. So these are about the wireless networks. Then these are some of the technologies that we are used in wireless networks. The Wi-Fi, very popular standard. Then Bluetooth, so used for short-range communications. WiMAX, similar to Wi-Fi but a larger scale, and ZigBee. Again, kind of short-range communication mechanism, which we don't see much of the people use, but still, if you have played with Arduino and very small gadgets like different IoT devices, then there you can there are components that you can plug and use the ZigBee communication, right? So some short-range communication mechanism. So we have different types of communication protocols like this, right? Then we can come to the data link layer. So as I told you before, uh, the data link layer is dealing with the hop-to-hop communication. It is not dealing with the end-to-end communication. So which means each and every hop might use a different technology. So within the network, so one hop might use wired network, then later on the other network might use wireless networks. So likewise, each and every hop might use different technologies. So for each and every communication technology or communication mechanism, they need to have a corresponding data link layer protocol. So Ethernet is such kind of protocol. So if you are using wired medium, then we can use Ethernet to do the communication. Then wireless, so it can be Wi-Fi or Bluetooth, such kind of a wireless network mechanism. Right? So there are different protocols like that. And you can see that I have put wireless LANs, so VLANs, so WLANs. WLANs means so wireless networks, wireless local area networks, and we can have wireless personal area networks as well, right? So like uh, like when we are using Bluetooth communications, it is wireless personal area networks, and we have don't think about this that much. We have sub layers in the data link layer, the logical link control and the media access control. So which is dealing with how to communicate with the physical layer and the communication with the upper layers. Then different topologies for this in the local area network. So we can have bus topology, ring topology, like as different topologies, and there can be full duplex and half duplex communication and different access control mechanisms. So that is a very important thing in the data link layer. I think you might have discussed these things in the network protocol lecture as well. So one of the major problem that the data link layer has to deal is this two types of links. So the data link layer, we have the point-to-point links and the broadcasting links. So it is something like this. So you can have two nodes like this and a single link connecting the two nodes. So there's nothing else in this network, only two nodes, and they are connected using a single link. So that is we called as point-to-point communication. So this is point-to-point communication. So this is one type of links. And there's another type of link that is the broadcasting link. So something like this, you have number of nodes like this. And we are using a single communication medium to connect those links, like a bus topology. Right? Now this is This is a broadcasting medium, right? So this is broadcast. So whatever the message that you send, let's say this node want to send a message. Let's say that this guy was to send a message to this. So it has to put the message to the broadcasting medium, and it will be delivered to all the people in the network, right? This is the problem with broadcasting networks. So data link layer has to handle these issues, right? So point-to-point link is straightforward. So whatever the thing that you put in the network, it should come out from the other end, right? So only two parties are there. So easy, you can have a serial communication. It can be clocked or unclocked. So whatever the thing, the message that you put from this end will be received at the other end, right? So this is easy. But this broadcasting networks is the problem, because when you add a message to the network, it will be delivered to all the parties. And not only that, more than one device can communicate at the same time. That is a huge problem that you have to handle in the data link layer. Let's say this guy is communicating, and while he's communicating, another one put a message to the medium. Then what happens? There'll be collisions, right? So can happen collisions here and there, and there will be noise in the network. So because of these collisions and the noise, nobody can use the network. The network become useless, right? So that is a huge problem in this broadcasting networks. So anyhow, the data link layer protocols has to handle this. So there are a number of protocols introduced to as a solution for this. Have you discussed Aloha protocol in your protocol lecture? Is anyone?
No, sir.
Okay, so then I will give you some brief introduction about that. So if it is a broadcasting network, so there are different protocols that we can use to avoid those problems, right? So one problem is that collisions. So collisions is a huge problem, because at one time more than one device can start a communication. So when more than one device is communicating, there can be noise in the network and collisions, right? So those two problems are there. So noise and the collisions. So what we are trying to do with this data link layer protocols is to handle that kind of issues, right? So one of the first, or one of the very basic protocol is Aloha. This Aloha protocol, and later on they have introduced updated protocol called Spotted Aloha, right? So two protocols like that. So Aloha protocol means, so once you get a message to the data link layer, it put the headers, and at once it forward to the broadcasting medium. Right? Aloha, very simple protocol. You get a message from the upper layers. At once you send it to the broadcasting medium. Nothing else. Very basic, very simple. Right? Now what happens if the more than one node has message to send? Other person also send a message to the broadcasting medium at once. So there can be collision. So they are not going to avoid the collisions. Collisions can be happen. So what they do is, once there's a collision, these nodes going to wait for some random time. So after waiting for some random time, they broadcast again. Right? So that's what they do. So somehow the messages will be delivered, and the efficiency of this medium is 18%. That means if you send 100 messages, only 18 will be delivered to the destination. A lot of collisions. Okay? So that is the basic protocol Aloha. And later on, they have introduced this slotted Aloha, which means each and every node has to start the communication in time slots, right? So the time is divided into slot. So all the nodes has to start the communication at the beginning of the time slot. Right? So by introducing that time slot, they have increased the efficiency up to 36%. That means if you send 100 messages, 36 will be delivered at the destination, right? So these are very primitive protocols, but they did the job at that time, right? So so all these two protocols, the Aloha and the Slotted Aloha, they are not going to check whether the medium is utilized or not, right? So they are not going to check whether the others are communicating or not, right? So that's why after that, it has introduced the other protocol, that is CSM, Carrier Sense Multiple Access. So in this protocol, before sending the data, they are going to check whether the medium is using or not, right? So without sending the message at once, they are going to check the medium is using or not. That means if the device here that someone else is communicating, or if the node is detect that someone else is communicating using the broadcasting medium, they are not going to send the message. They will wait, right? And after waiting, they will send the message back again. So that is carrier sense multiple access, right? So it has improved the efficiency, but still the problem was not solved. Whiteboard then wrote. Can you see my whiteboard? Okay, so we had Aloha, right? Then the slotted Aloha. Then, so in Aloha and the slotted Aloha, uh, the the devices, so once they have a message, they simply forward it to the physical medium, right? So the collisions can be happen, and the Aloha, the efficiency was around 18%, and here the efficiency was around 26%, so 36%. Then the next technology we can discuss is the CSMA, that is carrier sense multiple access. Right? So before sending the data, what they do is simply check the medium. So if the medium is idle, they are going to send the message. So if the medium is utilized by other nodes, then they are not going to send the message. So that is CSMA. So still the problem was not solved. The reason is like this. So let's say we have several nodes A and B, C, D. So we have several nodes, right? And so I will draw a line downward. So this is the timeline, right? This is my timelines in the networking domain. The time will be flow downwards, right? So let's say we have our timelines like this, and node B want to send a message. Now what the node B does is carrier sense multiple access. So node B at first stage, node B will check the medium, right? So it checks the medium. So there's no communication. So what B does is start the B's communication like this. It will be something like this. Broadcasting, right? So this broadcasting. Now I told you this downwards, we have the time, and it takes some very small time period for a message to deliver from one node to the other. So it is not at once delivered, right? So there's a latency. So that's what we are always talking about, that latency, because when you send a message from one device to the other, it takes some small amount of time to deliver the message, some milliseconds. And so based on the network medium. So if it is say Ethernet communication, right? It might be 1 millisecond, 2 millisecond, right? So small time period. If you consider satellite communication, then it will be 200, 300 milliseconds. So the delay will be high, right? Now there's a delay, right? So this is a single broadcast in medium, right? And we have 4 nodes. So B want to send a message, right? So before sending the message, B checks the medium, that is carrier sends multiple access. So B checks the medium, and no one is communicating. So according to the protocol, first you have to check the medium. If the medium is idle, then you can forward the message, right? So that's what the protocol says. So B done his job correctly. So it start the communication, right? Now it takes some time to complete the task like this, right? Now this is B's communication, right? So B start the communication at this T0 time, and it do it up to T, let's say T 10 time, right? 10 milliseconds it has done the communication. Is that clear? To check the medium, start the communication. So now this is B's communication. Is it okay? Is this diagram clear to you?
Yes, sir.
Okay, right, thank you. Then what happens is C also want to do a transmission. Now what C does is check the medium. So at this moment, So this is, let's say, t equals 2 milliseconds, right? And this is t equals 0, right? T equals 0 milliseconds and t equals 2 milliseconds. It checks the medium, and still this message didn't deliver to C. So when C checks the medium, no one is communicating, right? So according to the protocol, then C can start the transmission. So C start its transmission. Now this is C's communication, right? C also starts its communication like this. Then this is the C's transmission. Now what happens? So nobody has done wrong here, because according to protocol, what you have to do is check the medium before transmitting. Both the devices check the medium, and they haven't feel anyone else is communicating. So they start their transmission. But still, we have collision. So this entire area is collided, right? So this is collision. So whatever the message sent from C and whatever the message sent from D, both are useless because the messages were collided. Now is it clear? So CSMA is also not that good because of this problem, because of the delay. So we have some propagation delay from here to here, right? So that will be milliseconds of time, but that milliseconds counts, right? So we are wasting this much of time of the medium. This t time is fully wasted. Because they are not going to stop their communication, right? Because it is colliding, so the messages are colliding, but they are not going to stop. Right? Now that's the point where they have introduced another technology, that is carrier sense multiple access with collision detection, right? So this collision detection part was not there initially. So they have introduced another part, that is collision detection. Now this is what happens after collision detection. Right? So let me delete these things. This is what happens. B checks the medium. No one is communicating at T0. Start the communication. C also check the medium at T equals 2. No one is communicating. At that time, B also start the transmission, but it doesn't came up to C's level. So because of that, C can't hear it. So C assume that no one is communicating. Then C start the transmission. Right? Now we have another component, that is collision detection. Right? So we are not just check the medium and start the transmission. What we do is we check the medium, start the transmission, and while transmitting, we are going to listen to the medium. That is collision detection part. So we are going to listen to the medium while transmitting. So B is transmitting and B is listening. C is transmitting and C is listening. Because C is listening to the medium, C will hear that someone else is also transmitting at this moment. Is it clear? Because C is transmitting while listening to the medium. So see here that someone else is communicating at this point. Let's say this is uh, t equals 4 milliseconds, right? So at t equals 4 milliseconds, be here that someone else is transmitting. Now what t does is it's going to stop the t's transmission. Now t will stop the transmission at this moment, right? Now there's no more transmission from C. Then B is transmitting and listening. So nothing up to this point. And at this moment, right, at this point, B hears, okay, someone else is transmitting, right? So B hears that someone else is transmitting. So what B does is, B stop the communication. Now this is the point where B stops its communication, right? Now that is collision detection. So with that, we can save some time, right? Now only this portion is wasted, right? So this will be smaller than that bigger t, because the devices are going to stop the communication while they hear another device is communicating, right? So that is the difference between CSMA and CSMA with CD, with collision detection, right? So is it clear for you? Is it okay? If you want more clarification, please let me know. Right. So that is carrier sense multiple access with collision detection. Right. Right. Then we have another one, that is carrier sense multiple access with collision avoidance. So collision avoidance is actually not for wired mediums; it is for wireless mediums. We'll discuss that in wireless networks when we discuss in the wireless networks. So there, actually, it is difficult for wireless networks to detect collisions, right? Because the listening part is not that practical in wireless mediums while transmitting, because yeah, our transmitter and the receiver at the same location in the wireless device, and the transmitting signal is very high and receiving signal is very small compared to these two signals, because the transmitting strength is very high at the transmitter level. So we have both the transmitter and receiver at the same location. So the receiving signal is very small. So therefore, it is difficult for us to check whether there's collision or not. So therefore, it is not practical. And that's why we are using another mechanism called collision avoidance. So we are trying to avoid the collisions as much as possible in the wireless networks. And there's another mechanism to work with this broadcast. Actually, we have several high-level mechanisms like channel partitioning, random access, right? So channel partition means we are going to partition the channel for, let's say, time division multiplexing or frequency division multiplexing or code division multiple access. So we have different methods to partition the channel. And we have random access protocols, so the Aloha, Threaded Aloha, carrier sense multiple access. All these things are random access protocols, right? And token ring is uh, a ring passing protocol where we have a token, and once you have that token, you can do the communication. So that is another way of access control mechanisms, right? In the network. So this is the data link layer frame, and you can see the data portion. So this data portion contains the network header, the TCP header, and the data from the application. So everything is included inside this data portion. And data link layers, we have the header and as well as the tailor. So normally you won't see a tailor in other protocol levels, but in the transport layer or in the network layer, you won't see a tailor. So in this tailor, we are actually having a CRC check, right? So that is check whether there's some issue or error in this entire message, right? So there are CRCs or checksums in the headers. So you will find CRCs in TCP, UDP, IP. So most of these headers you will see a CRC. So that is for the only for the header section, right? So in this case, you are checking the checksum for entire frame, right? So that's the difference. So that's why you have it at the end of the message. So there's a checksum at the end of the header. Actually, there's a reason for that because we are in the data link here, we are dealing with this hop-to-hop communication, right? So from one hop to the other, we are dealing with that hop-to-hop communication. So within one hop, if a bit flips, right? That means if binary 0 becomes 1 or binary 1 becomes 0, that will be error. So there is no use of that message after that. If a single bit flips, then there is no use of the message. Right? So entire 1 GB of data will be useless if you flip one bit, right? So because of that, in the data link layer, we are dealing with hop-to-hop communication. So in each and every hop, we check whether there's an error. So if there's an error, we are not going to propagate that message with errors to the end device because it is useless. We are wasting the resources. So if there's an error, simply we drop the message. And the upper layers, like the transport layer, has to deal with the missing messages. And so they have to retransmit it again. But what the data link layer does is it simply block the message or drop the message if it has an error. So we are not going to propagate that erroneous message to the end or to the destination devices. They are going to drop it at the place that we identify that there's error. Right? So that's why we have this tail in the data link frames, right? Mm, right. Then this is the structure of the Ethernet, right? And another question. So did you discuss about Ethernet in your protocol lecture?
No, sir.
You haven't discussed Ethernet. Okay. So the Ethernet is the data link layer protocol. And this is the header structure for the Ethernet, right? So you can see that there's so all the in each and every net protocols like so I have only the Ethernet header, right? So each and every protocol we have this different information, right? Control signals contain, right? So the data part contains everything comes from the network layer to the data link layer, right? And these are the control signals that you put in the data link layer protocol. So Ethernet is this protocol, and we have a preamble. That is the first part in the data link layer protocol. So preamble is actually 8 bytes, right? So this preamble contains 8 bytes. So it is not small, right? So it has 8 bytes. And this 8 bytes, the first 7 bytes, that means first byte to the 7 byte, it contains something like this: 1010101010. Now this is the message contained in all the 7 bytes, right? And in the last 8 byte, it has 10101011, right? So you have 7 bytes with this 101010 and 108. It's right. So you have 10101010 pattern for 7 bytes, and last byte you have 10101011. Now this is what you called as the preamble. The reason is now we are communicating with 2 devices, right? So Ethernet or the data link layer protocols are dealing with the communication with hops, right? So from your machine to, you are sending the message to the, let's say, the router or a switch, right? Now there is no synchronization mechanisms in these protocols, right? So we are not going to time synchronize each and every device likewise. So this is the only synchronization mechanism that we have. So you send 10101010 for 7 bytes, and the destination might somehow calibrate to it, right? So 101010 pattern. And after that, in the 8 byte, you send 101010 and 11, saying that the preamble part is over. Then we are going to start the destination address, right? So that is the reason of having a preamble of 8 bytes, right? So first you send 101010101010 pattern. So the destination will read 1010101010, and at a certain point it read 10101011. Then the destination knows that after this 11 you receive the destination address. Is it clear? So it simply says the start of the information, right? So 1010101011 means you are going to start the destination address, right? Then you have the source address. Then in some versions of Ethernet, you have type here. And in some versions of Ethernet, you have length, right? Because you can't do some drastic changes in these protocols because there'll be a lot of legacy devices using old protocols. So you can't change the protocol drastically. So there are some versions which use this as type or some use as length, right? So don't think about it that much, but this might be different in different protocols. Then data from the top layer. And there's another important thing, that is padding, right? So I don't know whether you can remember, right? In the morning, I told you that in the protocols, there's a maximum size. And in Ethernet, we have a minimum size as well, right? So that is because you want to avoid some collisions, right? So in that case, you need to have a minimum size. So I'm not going to discuss why is there a minimum size and all the things, right? So the minimum size is there to reduce the collision. So in that case, if your message doesn't have enough size, then you can use this padding to increase the size of the message, right? So that's why you have a padding, and then the checksum. So this is the Ethernet header. So you might think that why I am discussing these headers that much, because later on we have to use SCAPI. So in the SCAPI, we need all these headers, right? So that's why I'm discussing about these protocols again, right? So you might have discussed these things before, but I'm discussing all these things again before because we need these protocols and protocol headers to work with SCAPI, right? So that is the Ethernet header. And so these are just the MAC addresses, right? So MAC address has 6 parts like this, right? So the first 3 sections are coming from the organization. So if it is the manufacturer is Intel, then this is for Intel. If the manufacturer or whoever the device manufacturer is, let's say Samsung or Apple or whatever, so they have their own part here, and the rest will be assigned by that manufacturer, right? So that's how they're trying to maintain this um, uniqueness of the MAC addresses, right? And yes, the layer 2 addresses and layer 3 addresses. So this is the difference between layer 2 and layer 3 addresses. So in layer 2, that is MAC addresses, Ethernet headers, you will find the destination MAC address first and then the source MAC address. So if you go to the L3 or L4 headers, first you will see the source IP, destination IP, or source port, and then the destination port. So in L3 and L4, the source comes first, then the destination. But in L2, you will see the destination first and then the source next. Again, there's a reason for that because in switches, we have the technology called cut-through switches, right? Cut-through and store and forward switches. So 2 types of switches technologies. So in the store and forward, the switch waits until the entire frame comes to the switch, and then it will forward it to the destination. And there's another method that is cut through. In the cut through switches, they read only the destination address and simply forward the message to the destination. So they are not going to wait until the entire frame comes to the switch. So to do that cut through switching, you need the destination address first. So that's why you have the destination MAC address in the first place of Ethernet headers, right? So again, some information about the protocols, right? This is about the switching. So I told you that in switches, you don't have MAC addresses, right? In the switch, there is no MAC address. If the switch is actually a programmable switch, then you need to connect to the switch. In that case, that console port might have some MAC addresses, but unless all switch gears, they don't have their own MAC addresses, right? So they represent the MAC address of the device which is connected to it, right? So it has a table, MAC address table. So it keeps the port number and the MAC address of the respective device which is connected. So for the port 1, if the device sees this, then it keeps an entry in the table that port 1 has this MAC address, port 4 has this MAC address. Likewise, it maintains a table, and so they collect this information from the messages coming from the device. So once this device sends a message, it recorded by just checking the source MAC address of the frame. So they will maintain that table, and time to time they will update it. And there are some attacks related to this table as well. So someone can poison this table, right, and do some attacks. So likewise, this is how the switching happens. So this is one screenshot of the MAC address table. You can see that the port, this is fast Ethernet port 1, and this is the MAC address of the device which is connected. And so you can see that is dynamic, right? So port. So these ports have the MAC address of the device which is connected, right? So I have took it from this, right? So Right. So I'm just going through these protocols. Yes, Ashan, a question.
Yes, sir. That MAC address table is subject only data with one hop, or the entire network data is there.
No. It is not a routing table, right? So that MAC address table, it keeps so it keeps information about that particular broadcasting domain. That's all.
Ah,
It is in the switch, right? So if you are using a manageable switch, let's say a Cisco switch, then you can see the MAC addresses of the devices which are connected to each and every port, right?
right.
So it is simply a table which has the port number and the MAC address. Actually, you can do some attacks on that, right? So you can poison that table, or else, and if there are some loops in the network, so normally we have that span protocols running in the network, so we'll discuss about STP later. So if you don't have that kind of span protocols, then the Ethernet frames travel through the network, it loops, right? Because there is no TTL in the Ethernet header, right? So
Yes, sir.
therefore, the messages will loop throughout the network and it will poison this MAC table, right?
No.
So there are some issues like that as well. So it keeps only the details about its own network. That's all. It is
Ah,
not like a routing table.
okay. Thanks.
So protocols, we have discussed these things before in the morning. Routing protocols and operations done by the network layer. So network layer, it do the addressing, encapsulation, the routing. So those things will be done by the network layer protocols. The IP. So some characteristics about the IP protocol: it is connectionless, best effort, media independent. So connectionless means, you know what it means, right? you you are not establishing a connection between the source and the destination before sending the data, like in TCP. So in TCP you establish a connection before you send the data by using the TCP three-way handshake. So TCP has some assurance that someone else is there at the other end. So there is no guarantee that it is the real destination that you want to communicate. So that's another story. But TCP has some assurance that someone else is there. So that assurance is there with TCP. So that is the connection oriented protocol. But IP, there is no such kind of a thing. So you simply put the destination IP address and send the message. So it can be delivered or not. Right? So there is no guarantee that someone else is there at the other end. Right? So connectionless, best effort. So it will send the message. It is delivered, then it is delivered. That's all. Right? So media independent. It doesn't matter whether you are using fiber optic, coaxial cables, whatever the twisted pair cables, or any kind of wireless mediums. It is independent of the media because these are in upper layers, right? This is, we are talking about the third layer, right? So it doesn't matter what is the medium is used in the bottom layers, it use the same IP protocol. But that does not apply to the Ethernet, sorry, the data link layers, because if it is wired medium, then you have to use protocols like Ethernet. If it is wireless, you have to use Wi-Fi protocol. So it is media dependent, right? So based on the media, you have to select the protocol. But IP, it doesn't matter. It can be any medium. Right? You are using the same IP protocol. Right? Okay, message from. So what is the tool you mentioned that need PDU header detail knowledge? It is SCAPI. So we'll discuss SCAPI in the next week. SCAPI is it is not a tool kind of thing. It is basically a Python package, right? So by using SCAPI, we can create our own network traffic. So that's what we are going to do, and we can use it to create some interesting tools. It is a Python package, so we are using Python and use SCAPI to do some interesting things. Right? So we'll discuss that in the next week, right? Samir, is it okay? So just now, just search about SCAPI, no problem. And so we'll discuss it next session. Right. Now this is the IP headers. Again, I'm giving you all these header details because for the SCAPI, we need the header information. So that's why I'm showing all these headers. So a lot of information are there, right? So as I told you, source IP address is first before the destination IP address in the IP headers. So a lot of information are there, datagram length, data, header checksum, right? TTL. Now the TTL is there in the IP headers, but you don't see TTL in anywhere else, right? So if something get looped, right, then it will be looped forever. If accidentally if you loop some Ethernet frame, then it is going to be looped forever, and there is no mechanism to stop it. Right? But in the IP headers, we have TTL. So the TTL is 10. Each and every time you go by a hop, it will reduce. And once it comes to 0, then that particular device is not going to forward it anymore. Right? So TTL is there in IP. So that is actually there to reduce that load in the network, because otherwise the messages will be looped again and again. So it will be travel here and there. Right? So TTL is there to avoid that. So IP version 4, there are some limitations. So we have very limited number of IPv4 addresses, and the end-to-end connectivity, there's no end-to-end connectivity, network complexity. So a lot of information, some information. So then we have the IPv6. So we have large number of addresses, to the power 1 to 8 addresses are there, right? And so it has easier some of the work, right? And now you don't need to use NATs, because initially we use NAT kind of mechanisms to reduce the use of IP addresses, the number of IP addresses reduced by using NATs. But now we have enough number of IP addresses with IPv6. So therefore, still we don't need that kind of mechanism, right? Okay, so routing will be, so there are different mechanisms to the routing. Either you can statically say that whatever the messages comes from this network, forward it to the other network. So likewise, you can put some static routes, and there's another way, that is dynamic routing. So there you are not going to explicitly say what to do. So you have some routing algorithms running. So they will do their own work and update the routing table. So a host can send message to different things, like to itself, or maybe to a local host or to a remote host. So all these things are handled by the routing. Right? So again, a few terms: the default gateway, default route, routing tables. So you might have come across these things when you are discussing about networks. So today in the morning I mentioned about the default gateway. So if you want to go out from your network, then you have to go through the default gateway, and there are some default routes as well. So normally we put some default routes to send whatever the messages through that route. and routing tables. All these routers, they maintain their own routing table. So that has some information. So if you want to go to this network, use this interface. So likewise, it maintains some routing tables. So this can be manually set up. So you can put some static routes and create the routing table, or else you can run some routing protocols. Let's say OSP, EIGRP, likewise routing protocols. And you can create these routing tables dynamically. Right, so that's what I showed you: static routing and dynamic routing. So routing table. Then the address resolution protocol, I mentioned you this in the morning. Right, so and I show you the demonstration as well. So the destination is in the same network, so it doesn't forward the message to the default gateway. We'll check the device within the network can get the MAC address and forward the message. And if the destination is out of your network, then it will forward that message to the default gateway. So it will find the MAC address of the default gateway and then simply forward it to the default gateway. So default gateway will then forward the message to the next network. Yeah. So these are some few examples. So if the destination in the same network, it will forward the message to the switch, and switch will forward it to the destination. Again, they use the ARP to find the destination MAC address. And if it is having you have to send the message to the remote network, then you have to forward the message to the default gateway, and it will forward back to the next network. Right, so transport layer protocols, the TCP, UDP, so very interesting protocol, that is TCP. So TCP is one of the best network protocols available. Right? So all of us are using internet because of TCP, right? So otherwise there'll be no internet. So it is very fair protocol, right? So it deals with a lot of issues in the network, and it try to provide the best service to the applications, TCP. So it initiates the connection before sending the data. So it uses that TCP three-way handshake, right? So it sends the SYN message to the destination and receive the SYN acknowledgement, synchronization acknowledgement, and then again send back the acknowledgement message and establish the connection. So it ensures the reliable delivery, which means for each and every segment, it send a acknowledgement message. So with that, the sender knows that whatever the message is delivered to the destination, that is the reliable delivery. Right? And the same mode of delivery means it doesn't guarantee that the messages flow in the same order, but somehow at the receiver's end, it reorder the messages and give the messages in the correct order to the application. And it has flow control, so which means it is not going to send one segment at a time. So based on the network characteristics, it send more than one segment at the same time. So it will increase it exponentially. Like first it will send one segment, then two segments, then four segments, 8, 16. Likewise, it increase in an exponential way. And once it detects that there's a collision or a congestion, then it stops there and again come back to a stable level. Right? So there are different congestion controlling mechanisms, slow start kind of mechanisms, and we have different TCP variants like TCP Reno, TCP Tahoe, TCP Vegas. So likewise, we have different TCP variants. So they handle the congestions in different ways. Right? So each and every TCP versions, they have different performance levels, right? So different congestion control. So TCP is very advance the protocol in that sense, right? So this is the TCP header. We have source port and the destination ports, sequence numbers, acknowledgement numbers, right? And a lot of flags, the urgent, acknowledgement, push, reset, sync, the resynchronization, finish. Likewise, it has a set of flags. Then options, option field, right? So option is there to send some extra information, right? And the receiver window. So that is, it says how much window is available at the receiver, right? The header length. So a lot of information are there in the TCP header. So very, very interesting protocol. So if you haven't go through it, just read about TCP. So very, very nice protocol. So this is the TCP three-way handshake. So before sending the data, it send a synchronization message and the destination will send back an acknowledgement. So with this three-way handshake, they actually calculate the RTT, right? So how much time it take for a message to deliver at the destination and get the acknowledgement. So it measures the RTT, and based on the RTT, it can get some information about the network. So this is the basic RTT of the network. So if the RTT is very low, then the sender can assume that it has a good performance in the network. But if the RTT is very high, then the sender knows that it takes a lot of time to deliver the message, right? So based on that, it will adjust all the retransmissions and timeouts and everything. So that is that much intelligence, right? So three-way handshake. That is TCP. Then UDP, very basic protocol, right? You can see from the header, it has source port, destination port, link, checksum, and data. That's all. But this is the TCP header. You have a lot of information there. UDP, nothing, just ports, right? So UDP doesn't care whether the message is delivered or not, right? It simply sends the message to the network. So anyhow, it might be delivered. Sometimes it might not be delivered. So it doesn't care. So if you have a message that you really want to send, then you have to go with TCP. That's why HTTP like protocols, they use TCP at the transport layer protocol. But when you consider video transmissions, streaming like kind of things, then you can use UDP because the frames are lost. Then the segments are lost. It is no use of retransmitting them, right? So that's what you are seeing when we are having a Zoom meeting or Skype call. Some of the part of the message is missing, but you don't get it later on. So that means there is no retransmission. It is useless to do retransmissions in that case, right? So in that cases, you can use the UDP protocol. So it will send the message. There is no connection establishment or retransmissions or error detection kind of things. Right? So it will simply send the message. Very basic protocol. So in the transport layer, some information, the sockets, right? Sorry, the ports, right? Source port, destination ports, and we have kind of well-known ports and some registered ports and dynamic or private ports, right? So socket is a very important thing. So applications create sockets with the destination, right? If you want to create a communication with a server, then you create a socket. So socket is basically the combination of port number and the IP address. Right? So you create a socket, and through the socket you do the communication. Right? Okay, so yeah, that's all actually. The slide set sense. So that's what has happened. Check what was the room. So those are just some information about the protocols. What is this message? All right. So the reason why I did a very quick introduction about the protocols, because from the next week onwards, Right? From the next session onwards, we have to work with some other tools like, give me a second, like Scapy, right? So there we have to do some practicals as well. So I hope all of you have your laptops with you. So we will do some in-class activities and try to work with the Scapy in the coming week in the next session, and we'll start our the other concepts. So we had to discuss about the VLANs. We'll discuss about the span tree protocols and the security issues and problems related with VLANs, the span tree protocols, and how we are going to protect these the switchers, sorry, the hubs and switchers kind of things. Then we'll discuss the DHCP, right? So then we'll discuss about the TCP, the security problems related to TCP, because there are TCP flooding attacks, session hijacking attacks. Then we'll discuss about the ARPs, so how to do ARP poisoning, ARP spoofing. Then we'll discuss some tools like the EtherCap, Nmap, right? So there are a number of tools that we are going to discuss. What else? Then, if there is enough time, we will discuss about the onion networks, the onion routing kind of things. And we have to discuss about DNS, right? So DNSSEC and DNS and DNSSEC, right? So a lot of interesting topics are there. So I just want to brush up your memory about the network protocols and how the network works before going to some advanced concepts. So that's why I did this introduction session. So hope you got some idea. So I know that you have discussed these things here and there in your undergraduates and as well as in our master's program. So I just need to get everything aligned so we can, it is like a foundation, so we can do the rest of the work peacefully if you have this basic knowledge with you, right? So that's why I did everything very fast and just to give you some basic idea. So I will put these slides in the LMS. So if you have some lecture time, please go through these things and search in the internet and uh, just get some more idea about these protocols. So about TCP, the IP protocols, right? About the data link layer protocols. I have put some information in the slides, but you can search the internet and read more about it and try to brush up your knowledge about these network protocols, right? So I did this very fast because we have learned this in the first semester, and so that's why I discussed this thing very fast. But we have a similar course for the information security in first semester, so in there I take more time to discuss computer network part because they don't have a networking or network protocol lecture in their first semester. So network security is there in the first semester course. So in that case, we discuss basic networks a little bit in my paper. Because in the cybersecurity degree program is mainly focused on network related stuff. So you have more network knowledge uh, in your course. So that's why we have several network courses in each and every semester, right? So in this semester also you have two network courses, the wireless and the network security course. Previous semester also you had two courses, the protocols and the network design. So you have a lot of networking knowledge in the cybersecurity degree program, right? Okay, so please read about these things, and if you have any doubts, just put an email or bring it in the next lecture. And so this is my plan. So I'm planning to do network security on weekends. and wireless security on weekdays. Because wireless security, most of the content will be delivered by myself. So we can do it leisurely on weekdays. And the network security part, one portion is done by me and the other one is done by Kenneth, sir. So I'll try my best to complete my parts and hand over the lecture to him. Okay, so that's why I do it on the weekends. And there are some practicals. So we'll try to arrange some practical sessions. So especially for the wireless security, we have to do some network attacks. So we have to do it with real devices. So definitely we will arrange those practical sessions on weekends. Right. So that is the plan for this semester. So if you have any questions, you can ask. No questions. All done. Okay, then shall we wrap up today's session?